Hello class. This video follows the lesson on drawing a line of best fit. There was something that I meant to tell you in the last lesson that I forgot to go over, and that was some vocabulary for you. So I'm just going to quickly go over that and then we'll start this lesson. So I did want to just review with you positive and negative correlation. So not only does this have strong correlation and it's linear, but we could also add the word positive in here. So it has strong positive correlation. And this here has moderate negative correlation. To help you remember whether it's positive or negative, think about slopes. This is going up on the right, like slope would, it's positive. When it goes down on the right, it's negative. Okay, so we're on to 3.5. So not only can we draw a line of best fit, but we can actually calculate the equation or line of best fit, which is beneficial because it will help us to make more accurate predictions. And we're going to write our equations for a line of best fit using the equation y equals mx plus b. Remember that in this equation, m stands for the slope of a line and b represents the y-intercept. The y-intercept is where a line crosses the y-axis. Okay, so over here it looks like the y-intercept is under 10, maybe 7, 8, something like that. We'll see when we calculate it. Okay, so in example 1a, we want to determine the equation for the line of best fit. Now to save time, this line of best fit was already drawn. So if you had to do all this work on your own, you would start by making a scatter plot, figuring out what goes on the x-axis, which would be the independent variable, figure out what goes on the y-axis, which would be your dependent variable. You'd plot all your points that were given from a table, or maybe you've collected your own data and then you draw your scatter plot. Then you would follow the steps from the last lesson, 3.4, and you draw your line of best fit. Now, we're going to continue from there. So now what we want to do is we want to come up with an equation for the line of best fit. So step 1. You draw the line of best fit, and again, this has been done from you, and you're going to use the tips from the last lesson. Step 2. When you're doing this, you are going to pick 2 points on the line of best fit. Now this is very, very important. So you pick 2 points that are on the line. They have to be exactly on the line. So these points here are not data points. I'm going to draw them in red. You don't see that very well. They're 2 points that are exactly on the line of best fit. Now, the reality is, if you were doing this and the points weren't already given to you, I would pick 2 points that you are absolutely certain what their coordinates are. So this actually one, you're kind of guessing that's at 40, 43. This one here, because it's right at the intersection of the grid lines, it's easy to tell what it is. So this is a really good point to choose, the 70, 70. And if I was going to choose another point myself, let's see if there's another point that looks like it's exactly at the intersection of the grid. There isn't. Well, this point here isn't terrible because if that here is 30 and that's 20, this would be 25, and it looks like it's exactly at 25, 30. So that's not a terrible point to choose either. We'll just go with this one, however, since it's already been marked. So these are our 2 points. Write down your points xy. In xy form, your ordered pairs. So I put a little note here for you. The 2 points must be exactly on the line. So remember my tip, if they fall right at the intersection of the grid, those are good points to choose. So you pick 2 points and then you write down their coordinates beside it. And ignore all the rest of the data points. The data points are irrelevant. So for example, you don't want to pick this point or this point because they're not right on the line of best fit. The next thing that we're going to do is we're going to calculate the slope of the line, okay, of that line of best fit using the slope formula. Now there are 2 slope formulas that you can use. You could use m is equal to rise over run. That's when you draw this right triangle and you calculate the rise and the run, and m is equal to the rise divided by the run. But because we have these ordered pairs here, it's also helpful to just use the slope formula. So here's my first point. I'm going to label it as x1, y1. And my second point, I'm going to label it as, oops, that's supposed to say x, x2, y2. So one of the points is the 1s, the other one's the 2s. They both have the subscript 2. So I'm going to substitute this into the slope formula. So it's y2, which is 70, minus y1, which is 43. Over x2 minus x1. x2 minus x1. So it's 70 minus 40. 70 minus 43 is 27. And on the bottom I have 70 minus 40, which is 30. Now this particular fraction, when I reduce it to lowest terms, 27 over 30, I can divide the top and bottom both by 3, so that fraction reduces to 9/10. So that means the slope of this line is 9/10. That's step 3. Step 4 is we're going to find the y-intercept. By substituting m, the slope, in one of the points. Okay, so remember we have 2 points that we could choose here, either 40, 43 or 70, 70. We're going to pick just one of them, and we're going to substitute that 1 point in for x and y in the equation y equals mx plus b. And then we're going to solve for b. Okay, so to recap, we're going to take our slope and we're going to put it in this position. We're going to take one of our points, x and y, so let's say we chose this point here. 40 would go in for x, the 43 would go in for y. That would leave us with only one variable to solve for, allowing us to solve for b. So I'm going to take the point 40, 43, and I'm going to substitute the 40 in for x and the 43 in for y. Now again, you could have chosen the other point, 70, 70, and that would also work. So that's my point. And then my slope, I calculated that to be 9/10. So I'm going to do my substitution. So my equation is, for a line, is y equals mx plus b. In the m position, I'm going to put the 9/10. And what we have to do is we've got to solve for this b. Okay, so it kind of looks like the equation of a line, except for this is supposed to be a number. Okay, so in for the y, we're putting the 43, as we already discussed. Let me change the 9/10 to 0.9. It's okay to work with a decimal number. And in for the x, it's 40. Plus b. I'm going to work on solving for b. So I'm going to start by multiplying the 0.9 times 40. So 0.9 times 4 would be, 0.9 times 40 is 36. So we have 43 is equal to 36 plus b. And I'm trying to isolate the b, so I need to subtract 36 from both sides. 43 minus 36 is 7. And that's my value for b. Now, if we take a look at the graph, it should look reasonable. So remember we talked earlier that the y-intercept looked like it could be 7 or 8? We did find it was 7. So that's a reasonable answer. So now after I found b, I want to write the equation of my line. So the equation of the line is y equals, I'm going to write down that slope, so it's 0.9, or you could write down the 9/10, x plus 7. Okay, so you need a number in the m position and you need a number in the b position. That's your final answer for the equation of the line of best fit. Okay, so now what we can do with our equation is we can use that equation to make predictions or to interpolate and extrapolate. So B says, use the equation to calculate the exam mark of a student with 26% as their term mark. So if we go back up to the graph, the term mark is an x value and the exam mark is a y value. So let's jot down what we know and what we're looking for. So the term mark is an x value. And what I'm trying to do in this case is I want to determine that y value. So I'm going to use my equation of my line of best fit, which is y equals 0.9x plus 7, and I'm going to use that to solve for y. So in the x position, I'm going to put the 26, and I'm going to solve for y. So 0.9 times 26 is 23.4. And when I add those two numbers together, I get 30.4. So therefore, the exam mark would be about 30%. C. Use the equation to calculate the term mark when the exam mark is 58%. Okay, so again, the term mark is an x value and the exam mark is a y value. So this time we know the exam mark is 58%. That's a y value. And now we're trying to determine x. So you have to be a little bit more careful when you're solving here. So let's write our equation. Our equation is y equals 0.9x plus 7. And this time in for y, I'm going to put the 58. And we have to work on solving for x. So when I isolate the x, this is a two-step equation. I want to move things that are easy to move first. That 7's easy to move. I'm going to do the opposite operation, so I'm subtracting 7 for both sides. That cancels out and becomes a 0. 58 minus 7 is 51. So 51 is equal to 0.9x. And then I got to isolate the x. So this is attached by multiplication. I want to undo it by dividing both sides by 0.9. And 51 divided by 0.9 is 56.7 as my x value. So now I want to answer the question. So therefore, the term mark would be about 57%. We should always take a look just to make sure that these numbers look reasonable in our graph. So let's go back and check. So if we had a term mark of 26, does it seem reasonable that the exam mark would be about 30? Let's look. So 26, that's 30, 26 would be somewhere here, and yes, it does look reasonable. Let's check the other one. If the exam mark is 58%, is 57% a reasonable answer? So now let's look for an exam mark of 58%, so that's going to be close to the 60. Go up to our line of best fit. Whoops, it should be down here. And then read down. Yeah, that also looks reasonable, our answer. So we are doing it correctly, or it appears like we're doing it correctly. Okay, so now we are on the back. And I just want to teach you a little bit more about statistics. So when is a linear model unreliable? Well, a linear model would not be a good model when there are too few pieces of data. So that basically means that your sample is too small. So if you have a small sample. And again, there are rules in statistics that you need to follow to make sure your sample size is large enough. So any valid statistical study will follow very specific rules. When the model is based on data that are clustered together, like really clustered together, a linear model would not be reliable. If there's no correlation, you wouldn't use a linear model, sorry. And when there are outliers, you may not use a linear model because it wouldn't help you make predictions that are accurate. I'm going to just show you this from our last note. So, for example, when you draw a line of best fit that's influenced by that outlier or weighted by the outlier, there's not going to be very many points that we predict that will actually fall in that line. Almost all the points were below the line. So the other method where we ignore the outlier would actually be the better method. If you wanted to draw the line of best fit and make predictions, you'd see that more points would be closer to that line than using this as your model for your line of best fit. The other time, or the other situation where you wouldn't use a linear model or where it might be unreliable, is when the data does not appear to have a linear relationship. So for nonlinear data. Now, how confident can you be of predictions made from scatter plots? So we're going to talk about data spread and reliability. So a model with data spread over a small interval is less reliable than a model based on data spread over a larger interval. The farther we get from the main cluster of data, the less confidence we should have on predictions made from that model. So that's especially when you're extrapolating, you have to be careful. So let me explain that to you again. So if I'm using this as a prediction for marks, and let's go in this direction. So the further that, here's our main cluster of data, the further I am maybe in this direction, the less accurate my prediction will be. And this would also be extrapolating because I'm outside of that range of data points. And the last, for sample size and reliability, the more data we use, the more reliable the prediction should be. That's straightforward. And the last one, nonlinear data. Not all relationships are linear. Sometimes over a small interval, a linear model may provide a reasonable fit for nonlinear data, but it will not be reliable at the extremes. And that's it for this lesson. Have a good day, everyone.